Hey everyone, welcome back to Real Analysis. This will be part B of Lecture 8, and in the previous section we talked through the limit superior and the limit inferior, and in this part of the lecture we want to introduce the idea of a Cauchy sequence. So let's go ahead and jump into it. Okay, so we'll be talking about Cauchy sequences here. Right? And so obviously if you've gotten this far in your mathematical career/education, then you've definitely heard of Augustin Cauchy, right? The limit theorems, many of them, the idea of the limit, I believe, goes back to Cauchy. And certainly this concept of sequences of this particular type, which are named in honor of Cauchy, are derived from him as well. So let's talk about what a Cauchy sequence is. So we've seen in already how monotonic sequences, monotonicity of a sequence, we've seen how that can imply convergence, right? And so we know that if, for example, a sequence is bounded and monotonic, then it must converge, right? And so here what we want to discuss is actually another criterion that can be used to identify convergence without having to actually know the limit. I tend to think of this as almost an alternative way to think about the notion of convergence. And it's actually a really intuitive way to think about it as well. Right, so let's define a Cauchy sequence. So a sequence, piece of n, in R is a Cauchy sequence. It's a Cauchy sequence if for all epsilon greater than 0 there exists an n naught natural number such that the distance between p sub n minus p sub m, right? So the distance between p sub n and p sub m is less than epsilon for all n and m greater than or equal to n naught. Okay. So this is the definition of a Cauchy sequence. So the basic idea here is that a sequence is called Cauchy if you can find a natural. So if for any epsilon given, I can identify a natural number such that once I'm past that term of the sequence, that n naught term of the sequence, then the terms to follow will all be less than epsilon distance from one another, right? And they don't have to be successive terms necessarily, right? Just any terms, right? But obviously, if you're trying to minimize the distance, successive terms are the way you would want to look at it, right? But so a sequence is Cauchy if for all epsilon greater than 0, you can find a natural number such that two terms beyond that natural number must be within epsilon of one another. Okay, so let's talk through this criteria here a little bit. So the criteria where we say p sub n minus p sub m is less than epsilon, and we say this has got to be true for all n and m greater than or equal to n naught. You can kind of think of this as being equivalent to, I'll say this is equivalent to, right? There's another way to characterize it. I could say p sub n plus k minus p sub n is less than epsilon for all n greater than or equal to n naught, and k in n, right? So the nth term and the n plus 1 term must be less than epsilon. The nth term and the n plus 2 terms and n plus second term must be less than epsilon. So it doesn't matter how far apart these terms happen to be. If n is greater than n naught, they must be less than epsilon in order for the sequence to be Cauchy. Okay, and so kind of from this characterization, you could say that it follows that, you know, if p sub n is Cauchy, right? If p sub n is Cauchy, then the limit as n goes to infinity of the distance between p sub n plus k minus p sub n, this must be equal to 0. And that's kind of the bottom line. So basically what a Cauchy sequence is any sequence where the terms of the sequence must get closer and closer and closer together as we move further out into the sequence. That's very intuitive, right? I mean, if you've got a sequence and it goes like this, right? Once you get past a certain n naught, then the distance between the values of successive terms is very small, and increasingly so, right? Because this whole thing has to converge, right? So that's the idea. That's the idea with a Cauchy sequence. A very intuitive way, in my opinion, to describe a sequence that's converging. And I guess we haven't quite gotten there, but the next theorem is basically just exactly what I said. So every convergent sequence in R is a Cauchy sequence. Okay, this is a extremely straightforward proof, right? But let's take a look at it. I mean, you may have guessed as much, right? As I said, I didn't really hold back in just stating as much because it seems rather obvious. Right, but let's see a proof here. Let's see how this can be shown. So let's suppose that p sub n converges to p, right, which is a real number. Right? And let's let epsilon greater than 0 be given. Okay. Then, what can we say? For the given epsilon, there exists an n naught in n such that p sub n minus p is less than 1/2 epsilon. And this would be true for all n greater than or equal to n naught. That's just the definition of convergent, right? So if we assume p sub n converges, we get this, right? This piece is automatic. Now we can just pull off the triangle inequality. Remember the triangle inequality. So then the distance for p sub n minus p sub m, right, the absolute value of the difference between those two numbers, that must be less than or equal to p sub n minus p plus p minus p sub m, right? This is the triangle inequality right here, right? And we know that by the convergence piece, this is less than half an epsilon, and this is also less than half an epsilon, right? And so that's equal to epsilon. Now this is less than half an epsilon for each of these, only in the case where n and m is beyond n naught. Okay. Right? And so, of course, it follows then that this piece here is less than epsilon. Okay, and that's exactly a Cauchy sequence. So, very simple proof, right? Uses, just the basic idea of convergence together with the triangle inequality and gets you to the finish line extremely quickly. Okay, so every convergent sequence in R is a Cauchy sequence. So if a sequence converges, automatically it's Cauchy. Okay. So let's see what else Cauchy sequences have in common with bounded and convergent sequences. So we can also say that the following theorem, we can also say that every Cauchy sequence is bounded. Right? So the previous theorem said that every convergent sequence is Cauchy. Now what I'm saying is that if a sequence is Cauchy, it must be bounded. Right? So just to give you an indication, basically what we're headed towards is the idea that Cauchy and convergence are the same thing. Right? They're equivalent. Right? So we're going to get there. Every Cauchy sequence is bounded. Okay, let's prove it. Right, this one also is relatively straightforward to prove. It's got a trick or two, but actually the tricks we've seen. So let's let epsilon equal 1. Okay. By definition of a Cauchy sequence, right, there's going to exist an n naught, natural number, such that p sub n minus p sub m is less than epsilon, in this case 1. And this will be true for all n and m greater than or equal to whatever this n naught happens to be. Okay, and so here's what we can do. So therefore, with m equal to n naught, we can do the following. P sub n minus p sub m naught, p sub n minus p sub n naught. I'm going to use this same construction. That's less than 1, and that implies that p sub n absolute value minus p sub n naught is less than or equal to 1. Okay. And that implies that p sub n is less than or equal to 1 plus p sub n naught. And this will be true for all n greater than or equal to n naught. Okay. Right, so that's just, a little bit of shuffling of inequalities. All right. And so then what we can do is we can let m, right? Remember, we're looking for a bound here. We're trying to show that this thing must be bounded. We'll let m equal the max of 1 plus the absolute value of p sub n naught, or p sub 1, or p sub 2, or ... p sub n naught plus 1, right? These are the maxes, right? These are the largest values. And so if we set the max equal to the largest of these, then we're done. Then basically for all n, p sub n will have to be less than or equal to m, right? And so p sub n is bounded. So this just starts with the idea of what is the definition of a Cauchy sequence, and then it just kind of breaks this down, and you realize that your max can be pulled from a finite set of quantities, right? Which means the sequence must be bounded. Okay. All right. Very good. Very good. Next. We're marching along here. Let's take a look at this theorem. So we're getting closer. So if p sub n is a Cauchy sequence in R, so if p sub n is a Cauchy sequence in R that has a convergent subsequence, then the sequence itself must converge. How's that going to work? Right? So we've seen previously that you can have sequences in general that don't converge but have convergent subsequences. But what this theorem is saying is that if your sequence is Cauchy and it has a convergent subsequence, then the whole thing must converge. Right? So there's something about this characterization of a Cauchy sequence which is going to force the subsequence to the subsequential limit to be the overall limit. And so let's go ahead and prove this one also. These proofs are fairly short, but they're really great. I mean, this is the way to learn math, but these particular proofs are really great at showing you how these things are really working, and we're inching towards kind of the big theorem here. We're getting real close, right after this one, actually. Okay, so let's let p sub n sub k be a convergent subsequence of p sub n. Right, so we've got this thing. And we'll just say with p sub n sub k converging to this value p. Okay. All right, so let's let epsilon greater than 0 be given. Okay, and so p sub n is Cauchy by assumption, right? Since p sub n is Cauchy, there exists, and I'm going to denote this as n sub 1. Okay. So there exists n sub 1 natural number such that p sub n minus p sub m is less than 1/2 epsilon for all n and m greater than or equal to n1. Okay. Right, so that's the basically this criteria just applies to the overall sequence being Cauchy. And secondly, we'll consider the subsequence, and we'll say, and since p sub n sub k converges, we'll just consider the same, I'll say for the same epsilon greater than 0. We'll retain that epsilon greater than 0. So because the subsequence converges, there's going to exist a k1 such that p sub n sub k minus p is less than 1/2 epsilon for all k greater than k1. Okay, so kind of separately, let's think about the successive terms of the subsequence. Okay, and so we've seen this kind of trick before where we say, okay, then let's define an overall natural number, n naught, to be equal to the max of these two, n1 and k1. Right? What we're basically saying there is, however far we have to go out for n1, if k1's further, we'll go out that far. Or if n1 is larger than k1, we'll go out as far as n1. Right? So we just go out as far as we need to, right? Which is all fair. Okay, so n naught will be equal to the max of these two. And we'll choose n sub k such that k is greater than or equal to n naught. Okay, so then, so basically n sub k is greater than or equal to n1, and n is greater than or equal to n naught, right? And so then by the triangle inequality, again, we have the following. So p sub n minus p is less than or equal to, and we can just slot in the p sub n sub k. This is less than or equal to p sub n minus p sub n sub k plus p sub n sub k minus p. And we know that this is less than 1/2 epsilon, and this is less than 1/2 epsilon. Right, so that means p sub n minus p is less than epsilon, right? And so again, using the triangle inequality and using just basically you've got two setups. You've got the overall sequence is Cauchy, which gives you this piece here, and you've got the overall setup is Cauchy, which the overall sequence is Cauchy, which gives you part of the setup here, the p sub n minus p, and then you've got the other piece, which is the fact that the subsequence converges, which gives you the other piece, right? And so overall, the limit as n goes to infinity of p sub n must be p. That's what this basically shows right here. Okay, very good. And so that is the last theorem we need to do our headline theorem for this section, and that is this one. All right, so every Cauchy sequence of real numbers converges. Okay, and so you got both now. So if your sequence converges, it's automatically Cauchy. If your sequence is Cauchy, then it automatically converges. So they're basically like there's just two ways to characterize convergence. Right? You've got your former idea of convergence, and now you've got this Cauchy idea, which the two are just lie right on top of each other. So let's prove this one. This will be kind of a conversational proof. So let P sub n be Cauchy. Okay. Now the previous theorem, right? The previous theorems, one of them said that P sub n is bounded. P sub n is bounded. Right? We just saw that. And so therefore it must have a convergent subsequence. We saw that previously. Okay, and then of course from the theorem that just preceded this, right? So if a sequence is Cauchy and has a convergent subsequence, then it must converge, right? So we'll let this be item 1, this will be item 2, and this will be item 3, right? So 1 implies 2, 2 implies 3, and 1 plus 3 imply P sub n converges. Okay, very good. So kind of conversational, but hopefully you can follow that. All right, very good. Okay, I think I want to do one example. Kind of a tricky one, and it's a little bit involved, but I think given the fact that we've just gone theorem proof, theorem proof, theorem proof, I think an example might be kind of a nice thing to do here. This is a little bit of an involved example, but it'll take maybe 10 minutes to talk through. Let's consider S sub n, where the terms here are a little bit involved. So S sub n would be equal to 1 plus 1 over 2 squared plus 1 over 3 squared plus ... plus 1 over n squared, right? Where n is a natural number, right? So each of the terms is this sum of n plus 1 terms, right? So S of n is 1 plus 1 half squared plus 1 third squared plus ... plus 1 over n squared. S of n plus 1 then would be 1 plus 1 half squared plus 1 over 3 squared plus ... plus 1 over n squared plus 1 over n plus 1 quantity squared. Okay, all right. So what we want to show is that this is a Cauchy sequence. We want to show that S of n is a Cauchy sequence. Okay, and so what would two terms in the sequence look like? So in particular, what does this look like? So if I take S of n plus k minus S of n, what does this look like? Right? So I'll say then for k and n. Let's break this down. Let's break down what these terms would look like. Well, so this is just going to be 1 plus 1 half squared plus ... plus 1 over n plus k squared, like so, and then minus, right, and this is all positive, so we can drop the absolute value, minus 1 plus 1 half squared plus ... plus 1 over n squared. Okay, and so we can drop the absolute value because this is positive, that's positive, and this is larger than that. All right, this just has more terms in it than that, right? Okay. All right, and so this is equal to, well, this is actually equal to 1 over n plus 1 squared, right? Because the 1 minus the 1 is 0. 1 over 2 squared minus 1 over 2 squared is 0. So the only terms that remain are the pieces in this guy here that aren't in this guy here. So this is equal to 1 over n plus 1 squared plus 1 over, and I'll just put another one, n plus 2 squared plus dot 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 plus 1 over n plus k squared. Okay. Okay, now I'm going to say that this is less than or equal to something, right? But let's first talk about, let's kind of do a side calculation here, right? So I'm going to say notice that, right? Notice that. So if I have 1 over n plus m squared, that is less than or equal to 1 over n plus m minus 1 minus 1 over n plus m. Okay, now you may be saying to yourself, okay, where are you going with this? Okay, well, let's break this down. So why is this true, first of all? So because, right, this is true because 1 over n plus m minus 1 minus 1 over n plus m, we know that that's equal to, and I'm just going to common denominator here, right, n plus m minus n plus m minus 1 all over n plus m minus 1, right? And so up top here, this is n minus n, m minus m. So this is basically just 1 on top here. And you've got 1 over n plus m times n plus m minus 1. Right, so you got this thing. Now, notice that, right, note that 1 over n plus m times n plus m, this is less than or equal to 1 over n plus m times n plus m minus 1. All right, now why? Okay, so that might not be obvious. Well, the reason this is less than or equal to is because this denominator is slightly larger. Right, so dot, 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 this denominator is slightly larger. Okay. Right, so just notice this. Right, we need this for the next part. Right, so just basically this guy here, 1 over n plus m, quantity squared is less than or equal to 1 over n plus m minus 1 minus 1 over n plus m. Right, so this is a fact we need. So we need this piece here, and just to kind of give a little background, that's why that's true. Okay, so I'm going to flip to the next page here, and we'll restate a little bit of this. Okay, so just to restate, so we can have it all in one section. S over S sub n plus k minus S sub n, that's equal to, and I'm going to skip a step, that's equal to 1 over n plus 1 quantity squared plus 1 over n plus 2 quantity squared plus dot 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 plus 1 over n plus k quantity squared, right? And now I'm going to say that that is less than or equal to, that is less than or equal to 1 over n minus 1 over n plus 1 plus 1 over n plus 1 minus 1 over n plus 2 plus dot 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 plus 1 over n plus k minus 1 minus 1 over n plus k. Okay. And so the thing to notice here, this is where that previous piece is coming into play. Right, so that previous piece was this. 1 over n plus m, quantity squared, is less than or equal to 1 over n plus m minus 1 minus 1 over n plus m. That's what these are. Right, so this is 1 over n plus k squared. So this piece here is less than or equal to this piece here. Right, this piece here is less than or equal to this piece here. This piece here is less than or equal to this piece here. Right, so we just showed that kind of as a side calculation. So that's why I can set it up like this. And now the nice thing about this arrangement is, you may have already noticed, successive terms will cancel. So these cancel. I've got 1 over n plus 1 minus 1 over n plus 1. Those go away. This one will cancel with its neighbor. Something will cancel with that one. And so ultimately, this whole shebang is just equal to the first term, 1 over n, minus this last term, 1 over n plus k. Okay? Right? And so this guy here is less than or equal to this. It's less than or equal to 1 over n minus 1 over n plus k. Okay. Now, what happens to these guys? Well, here's what we can say. Since 1 over n converges as n goes to infinity, right? We know that's true. It's also Cauchy. Okay, 1 over n is Cauchy. Okay, so therefore, if that's the case, then given epsilon greater than 0, there exists an n naught natural number such that the distance between 1 over n and 1 over n plus k is less than epsilon for all n greater than or equal to n naught, right? And k in n, right? So it doesn't matter if it's the next term over or if it's 10 terms over, or if it's 1,000 terms over, right? This is true. So therefore, remember, this is just this, right? So therefore, s sub n plus k minus s sub n is less than epsilon for all n greater than or equal to n naught, nk in n. And therefore, S of n is a Cauchy sequence. Okay. All right. Very good. Okay, so that's those are Cauchy sequences, and so we've with that we are ready to, in the next lecture, start exploring the idea of series. Right, so we've been talking about sequences. Now we know a fair amount about sequences. We've been through some of the key results regarding sequences. Next up is going to be, we're going to start talking about series, right? So sums, infinite sums. Okay, and so we'll leave it there. All right, take care, everyone, and we'll see you in the next lecture.